Hey class, this is Mr. Hofstad, and I'm bringing you lesson 6 in unit 3, which is all about tension force. And this one is a bit of a doozy, I'll be honest. This is a long lesson, and it's a little bit of a weird, hard to grasp concept, especially when we get into pulleys. But there's a couple key things that we need to keep in mind. So, tension forces will always be the result of a rope or a cable, right? So whenever you have a rope, we know we're going to have a new type of force known as a tension force. So not sure if you're all aware of this, but you can't push a rope. Ropes aren't very good at pushing things over, but they are really good at pulling things. So these are going to be unique forces that will always be pulling an object. Tension of a rope or a cable can only pull an object, right? So it'll always be directed away from the object, right? So if we were looking at this one here, the tension force would be pulling that object away in line with that cable, right? And another assumption, we have the same tension throughout the rope. So it doesn't matter where I cut this rope with my bubble or this system that I've drawn in, right? The tension is constant throughout the rope. So we have the same tension right at this end here as we do closest to the object as we do in the middle. Throughout the entire length of a rope, the tension will be the same. And that's going to become really key when we start drawing in our different systems in this free body diagram and analyzing all of the external forces on that system, right? Because in our free body diagrams, we can't look at internal forces. All we can draw are these external forces piercing through our bubble. All right, so last assumption is the rope or cable has no mass, right? So this is pretty much just saying there's no force of gravity acting downward on the rope. The only force of gravity is acting on our object suspended by the rope. So this is a pretty good assumption. The mass of the rope will be so small compared to what it's supporting that the force of gravity acting on these won't have a big influence. It's a little bit of an assumption, but just remember that we're pretending that there's no force of gravity affecting our system from the rope. The only force of gravity is found on the object suspended by the ropes or cables. All right, let's try this first example together. We have this nice box. That's generally what we find with these problems. And it's suspended by two different cables, right? So I'm going to draw the free body diagram for the system of the box and the ropes. So we have our box here at 5 kilograms. We have one rope coming up and to the right, and they give us an angle of that, and another rope that's going just purely horizontally, right? And when we drew in the system bubble around this object, right? If we failed to do this and we just looked at the entire system, right? We have no external forces on this box other than gravity. So we need to cut through the ropes so we can start analyzing the tension force in each rope. So I'll call that force of tension 2, and this one force of tension 1. And they gave us the angle between our rope and that top surface as 63 degrees. Okay, so we're going to have to use a little bit of trigonometry to break that into its components, but let's just figure out what the question's asking us first. We're going to determine the tension in each string, force 1, force 2. Are there any other external forces acting on our block? Well, we are on Earth. This is going to be the most common one we forget about, the force of gravity. So as long as we're on Earth, we know that the force of gravity is equal to the mass times gravitational acceleration. All right, let's think about what's going on with our box here. It's hanging by these ropes, gravity's pulling it down. Is it accelerating up, down, left, right, or anything? Nope, right? It's just being suspended there. So we know we're working with Newton's first law. Acceleration is equal to 0. So our F net is 0. Right? And we'll stick with our regular coordinate system. We'll call it up, down, not northeast, southwest. So up is positive, down is negative, left is negative, right is positive. Okay, so we know force of gravity is acting down and it's not accelerating down, so there needs to be another force acting up, right? So I'm going to, I didn't leave myself a ton of room, I'll just do it in a different color here. I'll break this force of tension into two components for this first one here. That angle's a bit in the way. Let's try this again. So we have 63 degrees. We have our y component. So that's our rope 1 FTY and FTX. So we have an x and a y, a horizontal and a vertical component to this rope's tension force here. So let's analyze everything in the vertical direction first, because we have a known force of gravity here, and we know we have the 1y component in our rope 1. So we're going to look at the vertical forces, knowing that F net is 0. So we have FTY, which is that vertical component to this tension force in rope 1. And we have our force of gravity, which is down, is equal to 0. So that vertical component of rope 1 is equal to the force of gravity just in the opposite direction, where gravity will pull it down and this tension is pulling it up. And we know how to find force of gravity using the mass of the object and its acceleration due to gravity. So the force of tension in the vertical or y direction for this first rope is equal to 49.05. Right? 49 newtons is our vertical component. All right, now this is where we get into our trig. So let's look at this force in our first rope. We know that the vertical component is 49.05. We don't know what the x component is or what the hypotenuse is, but we do know that this angle here is 63 degrees. Okay, so we actually do need to, for the question, determine the force in this string, the hypotenuse, but we also need to determine the force in our second string, which is horizontal. So that's going to be equal and opposite to this one. Since we're not accelerating to the left or to the right, we're again going to use Newton's first law in our horizontal direction. So let's solve for this total tension force in rope 1 first. So that would be our hypotenuse, and if we're using this angle here, that would be our opposite side. So we're going to use our sine function. How am I going to keep this separate? We'll just do this. So we have our force of tension, the hypotenuse, is equal to the sine of 63 degrees, and that would become our opposite, 49, over our hypotenuse. We're solving for the hypotenuse, so we need to multiply. Sorry, sine of 63 is equal to our 49.05 divided by f of t. Right, so then to solve for this force of tension in rope 1, we're going to multiply both sides by ft1, divide both sides by sine of 63 degrees, not 630. Alright, so that tension in our first rope is equal to 49.05 newtons divided by sine of 63 degrees, which comes out as 55 newtons. And again, we can do a quick check to see that makes sense. The hypotenuse needs to have a greater value than our side length. So that makes sense. We did our division correct. Alright, we know this is the first tension force. It's acting at a diagonal. Now we need to look at our horizontal. Right, so we're looking for the x component of our first rope, which is going to be our adjacent side. So we can use opposite, that's the one that we didn't calculate, right, using trigonometry, so this is a more exact value. So I'll use opposite over adjacent. So my x component is equal to, or is found using tangent of 63, where our opposite is 49.05, and our adjacent is our x. So again, it'll be multiply both sides by the x component, divide by the tan 63, and we get our x component is equal to 49.05 divided by tan 63. Alright, I'll just write that here. So this is still Newton's first law. Our x component is 49.05 divided by tangent 63, which comes out as 25 newtons. And from our starting diagram, we can see that in our horizontal direction we have this second rope, which is all in the x direction, and this x component of our first one. So we know that F net is equal to 0, where F net has our x component of our first rope minus our second rope, which is 0. Those are equal and opposite. So the force of tension in our second rope is equal to 25 newtons, and that's left. So force of tension in rope 2 is 25 newtons left. Force of tension in rope 1 is 55 newtons. And that will be at our angle at 63 degrees below the surface, or you could do northeast, southwest. Okay. All right. And moving on to our next example. I think we got some more notes on pulleys before that, though. All right. Pulleys are a bit of a struggle, bit of a challenge. They're lots of fun, though. Some really good questions come out of these pulleys. This is really driving home the idea that the tension in the rope is the same throughout the rope. So the tension force, even on different sides of a pulley, will be equal. So different types of pulley problems we can come across. This is the most simple, where we have a single hanging mass, right? So the force of gravity on this first mass is the only external force on the system. Because if we're just looking at this cart here, it'd have a force of gravity acting down, and it'll have an equal and opposite normal force from last lesson between the cart and that surface. Alright, so our normal force and gravitational force will cancel each other out. They won't have any impact. Our cart is still accelerating to the right because of this mass. Right, so the system that we're really looking at here would be this entire thing, where the force of gravity is the only external force. Right, and once we find the acceleration of the system, then we could look at just that mass and find the tension in the rope, which would be the same at each point. That'll become more clear when we get into some examples. Right, so one hanging mass is one type of problem. An Atwood pulley, you'll see this in the lab, is a little bit different. We have two hanging masses, there's no cart, and the gravitational force on each of them will contribute to the entire system's net force. So there's two external forces, the gravity on mass 1 and on mass 2, pulling in opposite directions here, right? So whichever mass is greater will pull it down, but as it's pulling down, the mass of that second object will resist that motion, and it'll slow it down. So these ones can be a little bit of a mind bender trying to get our equations for it, but it all comes back down to being able to draw a good free body diagram and label all of the applicable external forces. All right, so when we're working with our one hanging mass, this is going to be the formula we use more often, right? I don't recommend memorizing these formulas, right? It's going to be a lot easier just to work step by step through our external force analysis. Same with this one, right? This will be the heavier mass, and you're going to subtract the force of the second mass from it, and then the mass of the entire system will be on the bottom there. Okay, but not worth memorizing here. All right, let's try this example together. So we have to predict the equation used to determine system's acceleration. So for this first one, we're going to have to look at the entire system. Oh, I skipped an example. I apologize. We do need to figure out how to determine tension before we can do this. So let's do this example first. Okay, so we're determining the tension in the rope, which we're going to use for the pulleys, but just in a second here. So we have two carts. Our first cart is 16 kilograms. It's attached by a rope to a second cart, which is 21 kilograms. There's two external forces being applied. So we have 400 newtons to the left and 530 newtons to the right. So when we're analyzing ropes, we need to remember to carefully choose what our system is, what we're drawing our bubble around. So for this question, we need to analyze both masses. Right, so we're going to draw our bubble around both to find the acceleration of the system. So when we find the acceleration of the system as a whole, that allows us to ignore the tension of the rope in between, because our free body diagram only analyzes external forces. So by drawing my bubble like this, now the tension in the rope is an internal force, and we're going to ignore it, because free body diagrams, again, can't emphasize how important this concept is, only determine or are only analyzing external forces. So it allows us to ignore internal tension force. So now looking at both masses together, both of these carts, we can ignore the rope, and we know that the F net is equal to F1 plus F2. So we'll use left and right, positive, negative, as our reference system. So the net force will be 400 to the left, and we're going to add 530 to the right. And that gives us a total net force of 130. And we know that the net force is equal to the mass times acceleration. So this is all Newton's second law. So if we're looking for the acceleration of the system, we're going to divide both sides by mass. So the net force on this system with both of the masses is 130 newtons, and the mass of them combined is going to be 16 and 21 kilograms. And we get an acceleration of 3.5135 meters per second squared to the right. All right, so that's the acceleration of both of these carts. They're both accelerating. I usually draw that dotted. Accelerating at 3.5 meters per second squared. All right, we know the acceleration of both of these together, right? Now we can determine the tension on the rope, doing a fun little physics trick by swapping what we're analyzing in our question. So I'll use black for the second part. Now you could analyze either this cart or this cart. I'm going to choose to analyze this one. So we need to find the tension using only one mass. So to find Ft, analyze only one mass. So we know the acceleration of that mass is 3.5135 meters per second squared. We know the mass is 21. Now we're looking at this cart like this. We have 530 to the right and the force of tension from the rope going to the left. Still accelerating at the same 5.3135 meters per second squared, and the same mass of 21 kilograms. So we're going to use Newton's second law. And two, in our formula sheet, there is another shorthand way to do this, to write that. So on this back side, we have our principles of physics. So uniform motion is our first one. That's going to be Newton's first law. Uniformly accelerated motion, which is unbalanced forces, would be Newton's second law, right? And we've got no theorem, no principle of physics for Newton's third law. It's more related to the second law. So Newton's second law could also be referred to as principle of physics 1. So using principle of physics 1, Newton's second law, we know that our F net is equal to the mass times the acceleration. So we have our 530 minus our tension force is equal to the mass of that cart, 21 kilogram, and the acceleration of the cart, 5.3135. All right, solve for this tension force. We're going to add Ft to this side, subtract this whole product from 530. And we will get, right, so solve for Ft. You could do it by subtracting 530 from the side and changing the sign, since this is now a negative Ft. We'll get 456 newtons, and that'll be to the left. All right, that is our determining the tension of the rope example, but we're not done there. Now we need to do something very similar, but using pulleys. So our example A here is a single mass and a single cart. So I'm going to work off the paper for this one. Hopefully you can still see it okay, but I don't want to redraw all of these carts. All right. Predict the equation to determine the system's acceleration. So right above here we see it should look something like that, but let's derive that ourselves. So let's first draw in the system we're going to have to look at to find the acceleration. So when I'm doing that, when I'm choosing what to look at, think about what would all be accelerating at the same acceleration. Since they're attached by a string, they're obviously going to be accelerating at the same speed. So now I need to draw in my external forces. So I have force of gravity acting on M2. Right, I could have a force of gravity and a normal force, but they'd cancel out on this one. So the only external force is the force of gravity and this force that's pulling the cart there. So we're going to have Newton's second law, or principle of physics 1, principle of physics 1, where we have the net force is equal to our mass times our acceleration. So the net force will have this force of gravity and this external force. So even though they're not technically in the same direction, one is still opposing the other, right? This mass 2 will be trying to pull the mass down here, and as it gets to the pulley, it'll be pulling the cart in that direction, right? So that would actually be the same force there. So sometimes in some of the solutions, you'll see that they're flattened out along the pulley, and now force of gravity isn't acting down, but it's acting to the right. That might confuse a couple of you, so I'll just keep it as drawn here for now. So we have a net force, which has our force of gravity pulling it down or to the right. And we have this external force, just this F. And that will be equal to the mass of the whole system, m1 plus m2, and the acceleration of the entire system. And the question wants us to determine an equation for the acceleration, so I just divide both sides by m1 and m2. and I'd get the acceleration is equal to Fg minus F over m1 plus m2. Right, and we could take this a step farther. We know the mass here is m2, 10 kilograms. Mass 1 is 5 kilograms. And force of gravity will be 10 times 9.81. So we have mass times acceleration for our force of gravity minus our force of 300 newtons. And we're dividing that by 10 plus 5. Right, and now we can actually numerically calculate what we got as 13 meters per second squared. Right, so we don't know what direction that's headed in until we take a look at our sign. So the force of gravity is going to be 10 times 9.81, which is 98.1. And this force acting on the cart is 300 newtons, which is a lot bigger. So the 300 Newton force is dominant, right? It's bigger than 98.1 newtons. And that will determine the direction. So it determines the direction and means that Fg is resisting. So that's the force of this 10 kilogram mass is actually going to just slow down this mass. So we have 13 meters per second squared accelerating to the left. So this 300 Newton force is bigger. It's our dominant force. This mass 2, which has gravitational force of 98.1 newtons, is going to resist that. It'll slow it down. So our net force would be 300 minus 98.1, right? And that would be going to the left. Or you could write it, right? 98.1 minus 300. We'll get a negative answer, which means we're moving to the left. All right, let's try our second one. Here we have a 10 kilogram cart, and it has two different masses attached to it. So that mass is bigger, right? 7 is bigger than 4. So we know that we'll call that Fg3, Fg2. We know that this force of gravity is bigger, right? Mass times acceleration. They have the same acceleration. The one with more mass is going to determine the direction. So Fg3 is larger, and that'll be our dominant force. When we look at the entire system and how it's accelerating, our only external forces are these two forces of gravity. Everything else is internal and can be ignored. This one's bigger. It's the dominant force, so it means we'll be moving our cart to the right. We don't know the value yet, but we know that we'll be shifting here. And if this is our dominant force, that means our 4 kilogram mass or we'll call that mass 1, M1, Fg1, is our resisting. Right, so it'll be slowing down mass 1. Okay, again, we need to calculate the actual gravitational forces of these two. So we have our 4 times our 9.81 and our 7 times our 9.81. And this total system will be accelerating to the right, so we have our principle of physics 1, Newton's second law, where the net force is equal to the mass of the entire system times the acceleration of the entire system. So our net external forces would be Fg3 minus Fg1 is equal to mass of the system times acceleration. We're looking for the acceleration. First we'll break up the mass into its parts, right? 4 kilogram, 10 kilogram, 7 kilogram, M1, M2, M3. All right, so the acceleration is going to be equal to this force of gravity 3, which was 7 times 9.81, minus 4 times 9.81 gravitational force, and divided by all of our masses added up, which is 4 plus 10 plus 7. Right, all three masses are accelerating, so they contribute to this net force. And that'll give us a total of 1.4 meters per second squared. And that'll be to the right. A little bit tricky, especially understanding where we're going to draw our bubble, what system we're looking at. So this example, we wanted to find the whole system's acceleration. So we're looking at the entire system. If we're looking for a tension force, we need to have a new system now. All right, I think that's it. Some of this homework is a little bit challenging, I will admit, but if we're just following those same steps, right, determining the acceleration of the entire system, right, for this example, we'd have to look at force of gravity 2, force of gravity 1. They give us the masses. We can find the acceleration of the entire system. Since this mass is bigger, we'll be accelerating right that way, and this will be our resisting force. So always always determine the dominant and the resisting. Right, and you'll subtract the resisting from the dominant force, right, because they're in opposing directions. All right, if this is one of the hardest lessons in the unit so far, that's understandable. This is a little bit of a challenging concept, and feel free to ask me any more questions, ask for any clarification, because this is not an easy one. Give it your best shot. Don't get frustrated with it. Just try to work through it nice and slow, and ask me if you do get stuck and if the online solutions aren't making sense, and I will do my best to clear up the error for you guys. All right, good luck with the physics. I hope that it treats you all well. We'll be finishing this unit next week. So good luck. See ya.